In this video, we're going to be discussing upper and lower bound rules. Sometimes this is also known as the upper and lower bound theorem for the real zeros of a polynomial. Now, these rules and theorem help us limit our search for real zeros of a polynomial. First, we define two key terms. So a real number b is called an upper bound of the real zeros of a polynomial if all real zeros are less than or equal to b. The real number a is a lower bound of a real zero of a polynomial if all real zeros are greater than or equal to a. So if we look at our rule, let's let f of x be a polynomial with real coefficients and a positive leading coefficient. Suppose that f of x is divided by x minus c using synthetic division. If c is greater than 0, and each number in the last row is either positive or 0, then c is an upper bound for the real zeros of f. If c is less than 0, and the numbers in the last row are alternatively positive and negative, 0 entries are going to count as a positive or a negative, then c is a lower bound for the real zeros of f. Now it's important to note that upper and lower bounds are not unique. Any number greater than b is also an upper bound for the zeros of the polynomial. Likewise, any number less than a is also a lower bound. The rules for finding upper and lower bounds are stated for polynomial functions having a positive leading coefficient. However, if we have f of x equals to 0 and negative f of x equal to 0, they're equivalent equations. Therefore, if f of x has a negative leading coefficient, we can just factor out the negative 1 from f of x and apply the rule for upper and lower bounds accordingly. Let's do an example. Given that f of x equals 2x to the 5th plus x to the 4th plus 9x squared minus 32x plus 20, determine if an upper bound theorem identifies 2 as an upper bound for the real zeros of f of x. Now we're going to use this with synthetic division. So first we're going to write this as a factor, which means that we're going to have this as x minus 2. And as we go to set this up, we're going to have 2, 1, 0, 9, negative 32, and 20. And what I'm doing here is I'm taking each of the coefficients of each term, and then notice that there is no x to the third term, and so in that case I have to put a 0 there to hold its place value. And we're going to be dividing that by our 2 right here, so by our 2. So we're going to go ahead and bring it down, multiply. 2 times 2 is 4, put it up, and we're going to add those. 5, 2 times 5 is 10, put it up, add it. We're going to 10. 2 times 10 is 20. We're going to add it, and that's going to give us a 29. And we're going to multiply 2 times 29 and get a 58, and add these and get a 26. And then 2 times 26 is 52. And we're going to add these, and we're going to get a 72. So here we see that our leading coefficient is positive. And when we look at the remainder, so this is our remainder right here, right? That's our remainder. Look at the remainder, and all of the coefficients of this quotient are non-negative. Thus, we're able to say that 2 is an upper bound for the real zeros of f of x. So now let's do it with a lower bound. So here we're trying to see if negative 2 is a lower bound. So again, as a factor, that would give us x plus 2. So we're going to go ahead and plug in those same numbers, except this time we're going to be using a negative 2 here. So bring down our 2, we'll multiply, negative 4, add it. 1 plus negative 4 is a negative 3. Negative 2 times negative 3 is a 6. We'll add those. Negative 2 times 6 is a negative 12. So that gives us a negative 3 when we add those. Negative 2 times negative 3 is a positive 6. And then we'll add those and get a negative 26. And then we'll take negative 2 and negative 26 and multiply those and get a positive 52 and add these and get a 72. So now we want to check to see if, well, we can look here and we see that it's not an all non-negative row. So here we're going from a positive to a negative to a positive to a negative. So this is looking pretty good, except then we have two negatives in a row, and that's a problem. So because the signs of the quotient do not alternate, we can't conclude that negative 2 is a lower bound for the real zeros of f of x. And so that's how you would apply the upper bound and the lower bound theorem, or the upper bound and lower bound rules, in order to help you know if a number was identified as an upper or a lower bound.